next speaker is Ray Dong.
Hello everyone, I'm Ray from the University of Michigan, and today I will introduce our work, Presynthesis. It's a program synthesis paper, and we're trying to explore a new dimension to scale up the program synthesis. This work is done at the University of Michigan with my collaborators Qingyue, Danny Ding, who is at the UT Austin now, and Zheng, Ruyi, and my advisor, Professor Xinyu Wang. So the question we'll ask here is, how do we better perform the synthesis? Previous works have pushed many fronts on this topic. So for example, they explore the different search algorithms, search space representations, pruning mechanisms, and ML AI-guided prioritizations. So all these are asked the same question, what to do during the synthesis? But we ask a different question here, when to perform the synthesis? So say you have a lot of resources, right, but you don't have it online so after the synthesis task is given. If you have resources before the synthesis task is given, what you can do? So in this work, I will introduce an idea called scaling up by offline pre-computation. We name it presynthesis because it happens all before the task is given. So let me set up the problem first. In this work, we are considering a problem program by example. So it's a long-standing problem in this community, and it can be a foundation to many different applications. So basically, the user will give an I/O example, for example, 0001 to 0110. So this is a bit vector. And the user will provide you a DSL. For example, in this DSL, you can keep adding 1, adding 2, left shift 1, and left shift 2. And you feed this to the synthesizer. And the synthesizer will return you a program that satisfies the specifications. For example, in this case, X left shift 2 plus 2. So the synthesizer here, what it should essentially do is to search over a program space. As the program space could be large, this procedure could be slow. One way to speed up this is to use abstract semantics to prune, and it's also well studied in this community. So basically, you have examples here, and you have abstractions. For example, here, the abstraction could be the last bit. The last bit of every value could be 0 or 1. And the idea behind this is that it can divide the program space according to the program's abstract behavior into a finite set. So for example, x plus 2 and x shift 2, left shift 2 plus 1 all takes an input with last bit 1 and output with last bit 1. So now, say our output is not ending with 1. So we can prune away the space. The idea is that it can prune families of programs without enumerating them. And abstractions have different granularities, as you may know, and finer abstractions can prune more. I showed you how to use last 1 bit, but of course you can use more bits, for example, last 2 bits and last 3 bits. As you use finer-grained abstractions, you can divide the program space into more pieces, because now you can distinguish different program behaviors. And when you prune them, you can leave fewer programs, and the search space will be smaller. Well, everything is good here. But it comes with a cost. So as you use finer-grained abstraction, although you can prune more programs, modeling the space itself is very costly. And our idea, before our idea, okay, so the total synthesis time equals to the enumeration time of the search space and the time to prune the search space, right? So as you use finer-grained abstraction, the enumeration time will decrease because you are enumerating less programs now. But the cost to prune the search space increases. So if you add in these two together, you will find the total synthesis time will first decrease as you use abstraction finer-grained, and then increases. This is because eventually the pruning cost will outweigh the benefits of the pruning itself. Our goal in this work is very simple. We want to use finer-grained abstractions, but we don't want to pay the cost too much. To realize our goal, our key idea is presynthesis. So we divide the synthesis procedure into 2 parts, offline part and online part. We define the online part as you see the specifications, right? And offline is before you see the specifications. So in our framework, the I/O example will query something from the offline, and then the offline will return a pruned set of programs. So that means something is pre-computed offline. What we pre-computed? First is we do the semantics modeling of the whole program space. It's like a database of programs and their behaviors. And also, we have a part called reachability oracle. So this is an index of this database, because querying the database is better to have an index to make it faster. And we call this presynthesis because we pre-compute it offline, which means that we can pre-compute this data structure without seeing any examples. Let me show you how we do this by some by some running examples. So to understand how our framework works, let me first introduce you what to do without the offline part. Right, so I'm using the same DSL here, the same example, and we're using the last 2 bits as an abstraction. If you visualize the search procedure, right, it can be visualized as building a graph. For example, the node here is the value, and each value is marked with a grammar symbol, so you know where it comes from. For example, the base case here is our input, last bit 0, 1, and 2 in the grammar. And the edge in the graph is DSL operators. It means that you apply the DSL operator to the input and left shift 2, and you will produce a value, last bit 0, 0. And you can keep applying it, and you get new values. After you apply every operators and saturate, you will get this graph. So this graph basically contains all possible programs and values we can get from our input, last bit 0, 1. And the synthesis actually is a graph query problem. You see the input here, and you see the output here. What we want is the reachable part between these two input values and output values. It contains all the programs that satisfy the abstract specification. So take a step back. Everything is done online, all right? So this is what we built in the step 1, but what's really useful is actually a tiny portion of it. So the question is that, can we get the useful part without building the representation during the synthesis? Because building the first graph, is very costly. I'm only showing the 2 bits here, but what if you use finer grain abstractions, right? If you use like 3 bits, 4 bits, it can only be larger. Let me show you our first component, semantics modeling. It's a database of programs and their behaviors. So the idea is to pre-compute the graph I showed in the previous slides. There are some challenges, of course. For example, you don't know any input-output examples, what you can build for, right? Our idea is that we build for all possible inputs, so that whatever your online task is, I can always get something from our offline built structure. And of course, all possible inputs are infinite, right? So our idea is to use abstractions to reduce the infinitely set of values to finite set of abstractions. So our idea here is that we pre-compute the search space for all possible inputs using abstractions. I'll show you how we do this. So this is the DSL I used before and the abstraction I used before. So the base case, of course, is that you construct the nodes for all possible abstract inputs and also some values from the grammar. And you can follow the procedure I described before. So you grow this graph by applying DSL operators. And you can keep doing this until saturation. I'm only restricting the depth to up to 3 because I want to make things finite and bounded. And then when you see the I/O examples, you know what to do, right? It's actually, you can abstract the input and output to its abstraction values. And then the search procedure is actually a graph reachability problem. You start with the input and get all the forward reachable parts from our inputs. And you get all the backward reachable parts from our output. So you intersect these 2 portions, and you get the desired useful part as I showed before. So extracting solutions here is actually a bidirectional reachability problem. Yeah, so this is the input, this is the output. So you're basically queuing this graph. What I showed you is how we build the offline thing, right? But if you do it naively, you do the naive graph querying, it will still be very slow because you still need to touch most part of the graph. So our second idea is to build a reachability oracle. It's like an index of the database to speed up the searching. So what it do is exactly to answer the query I showed before. So you give an input and output, and it will return a part that is useful. In our experiment, we encountered offline graph with about 500,000 nodes and 500 million of edges. And the reachability oracle is designed to answer bidirectional reachability queries efficiently. And I'll skip the technical details now, and please refer to our paper if you're interested. So since we moved the heavy computation to offline, and online is just a simple graph querying problem, we can use finer-grained abstraction, but without paying too much cost, and our goal is achieved. So let's talk about the evaluation. We implement our tool called Foresighter because it has the foresight of the search space as you build it offline. There are some key questions that you may concern. First is, how does Foresighter compare with baselines for different application domains? And the second question is, can Foresighter solve faster with finer-grained abstractions? We evaluate our tool on 3 different application domains: string transformation, matrix manipulation, and SQL query generation. Our tool can outperform existing tool on all 3 domains and is generalizable to more domains. I'll emphasize on the SQL query generation domain because it's the hardest and it has more than 3,000 benchmarks from previous papers. So this is the figure where it shows how many benchmarks can be solved within a given timeout. So for Foresighter, the top curve outperforms all existing tools. And the second question is, can Foresighter actually solve faster with finer-grained abstractions? Because previously the figures I showed is conceptual. So what about the real data? So this is a graph that shows how the normalized solving time changes with different abstraction granularities. So for the abstraction granularities, the leftmost is the coarse-grained one, and the rightmost is finer-grained one. And if you see the red triangle line, this is build everything online, right? The curve is like a U shape, as I demonstrated before. So as the abstraction granularity becomes more finer-grained, it will first decrease, but eventually increase dramatically. That's because the pruning cost eventually dominates the time. And for Foresighter, we can continue to decrease the total solving time as we use more finer-grained abstraction. So our goal is achieved. And using Foresighter, you can use finer-grained abstraction online, but without paying the cost. So in conclusion, we introduced this offline and online paradigm, and our implementation is evaluated to be reusable and available online. And we welcome you to check out our paper and implementation. And thank you. I'm ready to take questions.
I'm Zheng from UIUC. I assume that you have to do pre-computation for different domains, right?
Yes. So if you are given DSL and abstractions, I will need to pre-compute the graph for different domains. Yes.
I'm just wondering how costly that is.
Oh, how costly? So I do have some numbers. So for example, in our SQL generation domain, that's the largest problem we consider, right? So we take about 7 hours to build our offline graph, and we take about 5 hours for the index. And the final product of the offline graph is about 51 gigabytes. Yeah. But you may wonder, we spend a lot of resources here. Is that a problem, right? So our use case, imagine, is that we have some service provider and we have some clients. And the synthesizer is acting like a service. So basically, when you provide a synthesis service, you can pre-compute using a lot of resources. And when the client have their problem, they can just send the task here, and it will return the solution. So we don't really require a lot of resources from the client side. Yeah. Yeah.
Yeah, I really like this work. So one question I have is, like the program space is exponential as like you get more as the size of program gets larger. So
yeah.
I wonder if I've considered if we can build a database incrementally as we get more queries. So initially maybe we have a small database, but like then over time we can specialize the database to the workload we have. Have you thought about this?
Yeah, incrementally build the search space is, of course, a way to extend this. So in this work, I'm assuming that the DSL is given is fixed and the abstraction is fixed. But you can use more finer-grained abstractions or tune your search space based on your need. I think that's a future direction, very interesting, but we haven't considered in this work. Yeah.
I have a question. So I like to build, sometimes I build super optimizers.
Yeah.
And so, you know, we run into exactly the problems you're talking about.
Yeah.
So can I use it?
Well, I think the key problem is that you have to define abstractions for your superoptimization problem, right? So for example, here, the SQL one, we have some abstractions like the size of the table, the type of the table, but what's the abstraction in superoptimization? That's a problem, right? That's orthogonal to this work. But if you have a good abstraction, you can build upon our work.
Well,
yeah.
Maybe we should talk.
Yeah, sure, thank you.
Yeah, I have a question. What if, for example, in your DSL, you allow some expressions that can build from other expressions? For example, if statement, so basically condition can be nested from other statement also like this. So, and this recursion can be basically infinite if you want to like brute force it for search. So is approach going to be applicable for programs like this, for DSLs like this?
Yeah, so currently what I'm showing here is that we have a bounded DSL, right? So you bound the maximum size of the DSL, for example, the depth of the DSL. And I think your question is that what if you have, for example, recursion, something like that, right? Well, in our work, I think our representation, the graph, is better to be applied to this kind of without loop, without recursion. And if you want to support like more fancy, for example, loop and recursion, you may need to consider another representation. I think it's an excited future work, but we currently do not have a good way to handle the like recursions. Yeah.
So the paper of the project uses a program by example as a means to like verify like correctness of the like synthesized program that the presynthesis process goes through. Is this approach also compatible with using formal logic based requirements statements instead of just like individual like input output examples? And if so, like what would be required or what would be necessary of the like acceptance predicates and abstractions in order for the whole modeling process to remain like sound and complete when like deducing down to
what kind of a domain you're trying to consider? So for example, what's the specification you're trying to consider?
Just something that represents entire like sets of input-output examples by a certain pattern rather than just individual examples.
Yeah, I think we are not restricted to like concrete examples. Anything that you can abstract behaviors to a finite set, we can, and if you can write the abstract transformer, which stick to the abstract semantics, I think you can use our tool. Because all we need is abstraction and abstract transformer, you know.
Okay.
Yeah, and the mapping between the abstract value and the concrete value, or the specification. Yeah, we can talk offline.
Okay.
Yeah.
Okay, let's thank our speaker again.